Okay, we start now. Okay, Assalamualaikum again. So we have about 1 hour for this first revision. But for this 1 hour, I'll try to cover many things. To cover a topic that we have been taught during this semester. Bending stress distribution, deflection of beam, forces in the truss, deflection of truss, and column. Okay, and this is not the only revision class. Maybe I have another ones. It depends on whether you need more revision or not. Okay, we start with a question. We have only one question for tonight. A concrete beam ABC is supported by a truss system on a roller at point B and point C here. Okay, ABC supported at roller at point B and point C, and we have overhanging here. The beam is supported uniformly distributed load of 8 kN per meter. The size of the concrete T-beam is as shown. T-beam. The truss system is made of steel hollow section. The truss system, this is the truss system. So here beam, this is truss system, is made of hollow section 100 by 50. Question. Draw shear force and bending moment diagram of the beam. Calculate the maximum bending moment between point B and C. Bending moment diagram and shear force for beam ABC, and what is the maximum bending moment between B and C. Okay. Calculate the maximum bending moment stress, maximum bending stress at the cantilever section, and determine whether it is safe or not. Okay, so when the question is about safe or not, which means this is design. So when this is design, we have to know what's the properties of material, and also what's the dimension. Okay, so this is the structural and loading diagram. Okay, and more question. C. Calculate the maximum deflection at point A here. Deflection at point A for the beam. Calculate the force in the members and reaction at support of the truss system. Calculate the deflection of the truss at point E, point A members. The buckling capacity. And by using a factor of safety of 2.5, determine whether the truss is safe to carry the load from the beam. And so this is again question on design. When it is given this factor of safety, then this is the design problem, and we must know the material properties. And it is given here, young modulus of elasticity, E200, EC30. This is for concrete. This one for steel, S, and yield strength of steel, 250 MPa, and yield strength of concrete 25. So about this yield strength, as a civil engineering, we have at least to know what's approximately the yield strength of few material, engineering material. For steel material 250, for concrete 25, and for steel material we have high strength and mild steel and high strength. Ranging between 250 to 500. but for E value was still between 2 to 210. Concrete, but it's different E value. Okay, now back to the question. Shear force and bending moment diagram. So this is the diagram. I don't know whether you are now familiar with this solution. Because it is basic in civil engineering. Shear force and bending moment diagram. And you must not take long time to solve this problem in the examination. Okay, I'm not going to go into detail, but here, the very first thing that we have to know is equilibrium equation. Summation MC0, summation F0. In this case, we have Fy 0. In this case, there is no Fx because there is no horizontal loading. So we have two equations. How many unknown? We have 1 and 2. What's about the horizontal reaction here? There is no reaction. What's about here? Basically, there is a horizontal reaction because it is spin, but in this case, because there is no horizontal loading or there is no component of loading in horizontal direction, therefore reaction is 0. Therefore, we have two unknown, we have two equation, then we must able to solve this problem. So this is the shear force diagram. Remember, in the exam, you have to write this properly. What is VB? What is VB dash? And so on. This is some error here. And you must show this calculation. Not only this final answer. If you just go to the final answer 97 without any calculation, you won't have any mark. You must show the calculation because this is not a computer. We want to know what's about your understanding in solving this equation, this solution, this question. Okay, and then similarly BMD, bending moment diagram, to show each of the point A, B, C. Okay, and to show the calculation very detailed. Now, if the question is the maximum bending moment at a point here, so remember, during the first and second topic, maximum bending moment will occur at a point where the shear force is 0 or shear force change from negative to positive, or it is called contraflexure. This is the, not contraflexure. Contraflexure is here. So this is the point where shear force change from negative to positive. So somewhere here, but we do not know where. So use this triangular, identical triangular here. One triangular, one triangular. And we want to know A and B. Use this relationship. A plus B equal to 4. A plus B equal to 4. And on this triangular, A over 25 equal to B over 7. And we have A equal to 1 to 5 and B 0.875. Then what is moment? Mx dash equal to 36 here minus the area of moment diagram. The area of shear force diagram here. Yeah, and the area of the shear force diagram is 25 times 3 over 125 divided by 2. So the bending moment is 3.06 kilonewton meter. Okay, that's first question. Yeah, we have another 7 question. Okay, this is the second question on bending stress. Okay. So when we are calculating bending stress, what we should know here is I, moment of inertia I. Okay, and how to calculate I? Okay, I is I don't know if it is given here or not. Yes, yeah, this is I. Yeah, for this, in this case, we have how many segment? 1, 2 only. Yeah, 1, 2 only, not many. So it is easier for you, yeah, to make a table. Yeah, for each segment, y is the neutral axis. Yeah, from the reference line. This is reference line to each centroid. Yeah, of the section of the segment. Yeah, n is h. H is the distance from from the neutral axis of each element to the neutral axis of the whole element. Okay, what is the centroid of the whole element? You solve this part first. Yeah, you got ay, and then the summation here. Yeah, and yc is equal to this ay divided by a here. Yeah, 31 over 172. You got yc. So here is yc, about 181.5. Then once you got yc, then you know you can calculate what is h for segment 1 and segment 2. Yeah, okay, and then a squared here, a multiplied by h, then the summation 2609.4, and then this is the I. Yeah, I for ah squared. So I equal to 2609 plus this one. Okay, see? So if you are fortunate during the exam, I is given. But if you are not fortunate, then you have to calculate I using this table. Okay. Okay. Therefore, bending stress equal to my over I, or sometimes we call it m over z. One is y set to the outermost of the section. When you say outermost of the section or outer layer, the most outer layer is the here, top and bottom. So top is equal to 81 and bottom 368. Yeah. So we repeat again. Bending stress here is the stress at the most outer layer of the section. There are two most outer layer, top and bottom. So top will be in compression, bottom will be in tension. Okay, if bending moment is positive, in this case, bending stress. Okay, what is the question? Bending stress Which bending stress? Bending stress at the cantilever section and determine whether it is safe or not. Here, cantilever section. So when it is mentioned safe or not, that means we have to calculate the maximum bending stress along this segment here. Maximum bending stress. Okay, so sigma equal to m 36 times 81 divided by I 0.62, and sigma, another sigma is this one is for bottom 2.82, and this is compression, this is compression, here is tension. Okay, so allowable stress in compression is normally 25. Here is 0.62, so okay. And allowable stress in tension is 5. Here is 2.82. That means it is also okay. So the answer is the section is safe. Okay, third question. What is the deflection? What is the deflection at point A? So as we have done so far, that there are 4 methods of deflection. Double integration, Macaulay method, virtual work method, or unit load method, and the last one is moment area method that we have done last week, last Thursday. So which one you want to use? It's up to you. But if it is specified in the exam, in the question, then you have to use that method. But in this case, it is not. It is not mentioned. I don't know. Check. Calculate the maximum deflection at point A. So it is not mentioned which method. So you are free to use any method that you feel comfortable. That okay. So this is the formula. Delta equal to mm over EI dx. M is the bending moment due to the actual load on the real structure, and m small letter is the bending moment due to unit load on the virtual structure. So this is the real structure. Real structure. We have calculated the moment, and this is the virtual structure. For virtual structure, similar to thrust, unit load method is applied on the point that we want to know the deflection. In this case, A. If you remember, it is simple principle with thrust. Apply one unit load at the point of question, the point that it is required to calculate the deflection. So in this case, is point A. So due to the one unit load here, what is the bending moment and shear force diagram? Actually, what we need to know is bending moment diagram, not shear force diagram. This M is not shear force, but to calculate the bending moment diagram, it is easier for you if you draw first the shear force diagram. That's why it is shown here. And in this case, the bending moment diagram, the bending moment at point B is equal to 3. Calculated from here. 1 times 3 equal to 3. Okay, and we have reaction. yeah, reaction at B and C. So we have now both visual structure and real structure or physical structure. Then what next? Okay. Uh, Now this beam is divided into two, AB and BC. AB and BC. So we will calculate the energy, yeah, the work done on both AB and BC. Okay, where x between 0 and 3 and x between 3 and 7. Okay, and we have two, okay, two structural condition or two loading condition, actual loading or real loading. Another one is virtual loading or one unit loading. Due to actual loading, this is the loading diagram, and this is the loading diagram for virtual load. Okay. Now, once, yeah, you have shown this loading diagram, then derive the moment. Yeah, derive the moment for real structure and virtual structure. This is real, this is virtual. So for this one, it is 8x squared. Yeah, but for virtual, negative 1 time x. Similarly here, yeah, m equal to 8x squared over 2. Yeah, you have to uh, familiar with this derivation of moment. And for unit load method, oh sorry, for virtual load or unit load, m equal to what? -1. Why it is negative? Because it is, yeah, uh, counterclockwise. Yeah, 1. Okay, plus 704. This one is reaction. Okay. Mm. And now, yeah, you apply the formula for deflection, yeah, for each segment here. Okay, this is for segment 3 to 0. This one for 7 to 3. Sorry, 0 to 3, this one 3 to 7. Okay, 0 to 3, 3 to 7. Okay, so solve this equation. We got delta A equal to, yeah, 1 over EI and this energy equation. Then this is the answer. Yes, yeah, we cannot, yeah, go through each line, yeah, because it's too long. So this is the answer. And you see here, yeah, this is my comment. Too long, yeah, too long, and also, yeah, it is subjected to error and mistake, whether in calculation or in writing. So how do you feel? Yeah, are you comfortable with unit load method? If you are comfortable, if you are familiar with the methods, okay, you can, yeah, go on. But if you are not familiar or you are not good in, yeah, very long mathematical equation, integration, yeah, then you can change from right. Now this is from left. Yeah, this one from left. Now you can change from right. So for this one from change right, it is shorter, but I think it is not given here. Yeah, it is for your homework. Yeah, very long. Yeah. It is you are fortunate. It is given here from right. Yeah. So if you go from right, yeah, this is the formula. What the difference? M equal to minus 8x squared over 2. What is in here? Okay. Yes, similar. Then what's what this one? M equal to minus 7 plus 4x squared. M small letter equal to 3/4 over x. What's about this one? Too long. Yes, too long. Minus 8x squared over 2, yeah, and so on. So compare with when you start from right. Here is the formula. Short. So what's the advantage? Yeah, when we use short equation, yeah, so that yeah, it is not easy to make error or mistake. Okay, it's given here from right. Yeah, finish here 7.08. So you can try both, yeah, as your homework. What happen if you start from left? What happen if you start from right? Okay. Oh, it is also given here. Okay, Macaulay method. Yeah, Macaulay method. I think we have only another 30 minutes. So I'm not going to detail each line. This is your homework, and I'll give the copy to you and also this recording. Okay, Macaulay method, you use this equation. The difference between Macaulay method and the differential equation, sorry, double integration method is that in Macaulay method, you have this kind of bracket. What is this one? When you have this kind of bracket, that means you integrate anything in this bracket as if it is a variable. X minus 3. Don't yeah, uh, don't take this x out of this bracket. Leave it like this. Yeah, just integrate as one variable. X over 3 is one variable. This is the Macaulay method. Okay, go on. Boundary condition, you have C2 0 and so on. Y equal to 89.6 millimeter. Is it similar? Here, where is 7.08, and what's about this one? What is this? Delta A, and here y equal to 89.6. Different answer. Why different answer? I have to check. This one is 0.7.08. Here is 89.6. We have to check again. Okay, let us go to the next question first. Pause in the transition. Okay, first thing, for the indeterminacy of this trust system. Okay, 49 kilonewton. Where do you get from? This is from the analysis of beam. Yeah, 49 kilonewton. There is no horizontal reaction, therefore only vertical. Okay, about this trust system. How many reaction? 1, 2, 3, 4, 5. Yeah, 1, 2, 3, 4, 5. It looks like this indeterminate externally, but in this case, yeah, even though it is indeterminate externally, sorry, even though the number of reaction 5 is more than 3, yeah, but in this case, the force in the members can still be calculated. Yeah, okay. How to do it? Don't go to the reaction first. Go to the applied load. Can we start with B? Yes, because at B there are only 2 members. If the number of members is only 2, it is okay. But if it is 3, not okay. Yeah, in this case there are 3. 1, 2, 3. Here, yeah, 1, 2, but we have horizontal here. 1, 2, 3. Here, 1, 2, 3. Here, 1, 2, 3. So, yeah, you can choose B to start the analysis. Okay, join B, use the, what is this? Join method. F10, Fx0, then you have FED equal to FBE equal to 21 square root 2 here. FBG, sorry, FED, FBE. Yeah, here, BG, sorry, BG, yeah, BG. And remember, yeah, take note, if two trust members meeting at B and the angle of this trust member are similar, equal, then, okay, the force in the member is symmetry. In this case, BG equal to BE. Yeah, BG equal to BE. Then, can we move further? Yeah, once you have this, then you can go here. And what happened this one? Yeah, you see, uh, there are 3 members meeting at point E. There is no external load, and 2 members are collinear. Collinear means, yeah, on one line. So in this case, Fe equal to 0. Fe equal to 0. So don't wasting time to find Fe. Yeah, don't wasting time to develop this formula because there is no formula. Yeah, the member Fe is 0 force, which means FBE equal to FEH. Now, when you comes here to H, can you solve this problem? When you know FEH, that means there are 2 on the left. Okay? And when you have only 2, not 3, not 4, you can solve this equation. Finish. Yeah, so you finish here, 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 and here. What next? Reaction. So that means in this case, yeah, we could not find the reaction at the beginning of the analysis, but yeah, the reaction comes at last in this case. Okay, so without any, yeah, I don't have to go clearly in detail, then this is the calculation. Yeah, this is the answer. Yeah, VF0, HG21, VG28, yeah, and so on. Okay, what next? Buckling. Okay, calculate the bending moment of inertia Ix and Iy of this section. Yeah, you know that for this kind of section, you have minor axis and major axis. Yeah, minor axis and major axis. And about the minor axis, you have to calculate what is I. And about the major axis, you have to calculate what is I major. Yeah, here I. This is the formula. So I about Y is equal to 0.65. I about X is equal to 1.736. That means, yeah, IY, sorry, IX is larger than IY in terms of bending, buckling, yeah, and uh, deflected shape. Now, minor axis does not always the weaker axis. This is minor axis. Yeah, it depends on the restraining position. Even though it is minor axis, well, it depends on whether it is restrained or not. The rotation about minor axis. Yeah, if it is restrained, then probably the slenderness ratio, the slenderness is get classified as sharp. Okay, then in this case, how we got this photo from here? Yeah, this is line diagram. Yeah, but from line diagram, yeah, we can imagine what will be the orientation of the member. Yeah, the orientation of the member. Okay, so if this is the interconnection of member, then it is mean that here, yeah, it is restrained. Therefore, the slenderness ratio is based on BD. Okay. So restraint about minor axis at mid length, but it is not restraint about major axis. Yeah, it is not restraint. But it does not mean that it is weak. It depends on the slenderness of the unrestrained. I say this slenderness of the member. Okay, Lex Ley equal to 1.0. Yeah, for this one L over 2. Why L over 2? We have done it, yeah, last week. Sorry, last 2 week, yeah, on buckling. Okay. What is L? L equal to 4 square root 2. Yeah, this is your, I think you know, you know better what is length of each member. Here, 3 here, 4 here, and what is FBA? Yeah. Yeah. So if you use this slenderness ratio about minor and major axis, then we can calculate the P critical based on bending stiffness. Okay, so PCX equal to 107 and PCY equal to 138. Where in this case, PCY greater than 107. So the critical buckling load PCR is the lesser of PCRX and PCRY. Yeah, so PCR is 107. Okay, then what next? Okay, so the allowable compression load is 107 divided by factor of safety. Yeah, 2.5 is factor of safety. Hey, what is mean here is that uh, the the member can be loaded, yeah, uh, and initially we will load the member up to the failure, but at that moment, yeah, uh, the buckling capacity should this one, the allowable compression load is 107 divided by 2.5, 42.8. And the force in the member BD is 21 square root 2. Yeah, BD, yeah. Here, BD. BD, where is BD? Oh, here. BD. Okay. And since it is less than allowable compression load, that means it is safe. Okay. And now deflection of thrust. At which point? E. Yeah, at E. So this is the real diagram. Under the real loading, the question is what is deflection at point E? So when the question is about what deflection at point E, that means we can apply 1 unit load at E here. Yeah, and you see here, yeah, zero force member, zero force member. And what it is left here is compression member. Now, yeah, your works becomes easy now because the rest of the member are zero. Okay. So again, yeah, create this table. Yeah, create this table which will force U, P, L, and UPL. Okay. So in this case, if you don't want to create this table, it's up to you. Yeah. But for convenience, for convenience, we should create this table. Okay. And this is the final answer. Delta equal to 0.3 millimeter at which point? At point E. Yes, so remember, if the question is about deflection at point E, then yeah, we apply 1 unit load at point E. For the real structure, we just maintain point load at B. Okay. Okay, so that's the end of the distribution, which you noted here. It covers many things in one question. It can be like that, but yeah, uh, I think there is no question in the final exam, which combine all topics. Yeah, so the question is very straightforward, whether it is trust or beam. Okay, any question? It's 10:30 already now.
So far, so good, Doctor.
Okay, so I'll give you the copy, yeah, in PDF format, yeah, to WhatsApp group or to, I think, WhatsApp group, yeah. Oh yeah, in e-learning also.
Okay, Doctor, thank you.
Okay, any more question? No question, eh? Okay, so you wait for